I'm Mara Adams, mechanical engineering.
I'm Jocelyn Guitardi, electrical engineering.
I'm Taylor Golan, mechanical engineering.
I'm Daniel Williams, mechanical engineering. Our advisor for this project is Dr. Zhu, and we are the plate swapper.
So today we'll be going over what our project is, what it does, and how and what we've achieved this semester, as well as what we'll achieve next semester.
So just for some background about what our project is about, we're working with build plates on 3D printers. So build plate is a magnetic removable printing surface found on most Slinger 3D printers. When a print is done, you remove the build plate and you have to flex it in order to remove the print, and you put it back on in order to start your next print. So the problem that we're trying to fix is that you can't be by your printer 24/7. So it can take 2 days to print parts that would have taken 6 hours even to print consecutively. So whether you're a small business owner who wants to rely on printing for your product, or even just a 3D printing enthusiast who wants to print a bunch of parts, it can take longer than desirable to print a bunch of parts if you're not next to your printer every 2 hours to print a build plate. So some solutions to this problem already exist, one of which is a conveyor belt system starting around $1,000. Another is a Bambu Lab system only compatible with Bambu Labs printers, which is not currently sold in the US. So we want to create a solution that's both affordable and more universal.
So, the scope of this project. We want to enable continuous printing 24/7 with no human intervention. We are styling this robot towards the Bedslinger style of 3D printers, and we're just focused on removing the build plate. This project is not reprogramming a 3D printer, and we are not creating a custom slicer for it.
So this is a video of our completed CAD design. As you can see, our planks retreat and then come down to the plate, bring it over to where the printer would be. It then drops it on the printer, retreats, comes back, and picks up the plate once again, and then drops it.
So some specifications we wanted to follow when creating our design were that the plate swapper must be able to remove a build plate from the printer. It must be able to grab at least 2 different types of build plates. It must include space for the completed build plate to go when it's done. It must be able to place a new build plate onto the printer, and it must be able to complete this action 3 times using each of the build plates in our spring stack.
So this right here is the clip. The green is made of 3D printed material, and the red there is a limit switch. It's designed to clip onto a 20x20 aluminum extrusion found on the top of most Bedslinger style 3D printers. So when your printer is done, it will hit this limit switch, telling our robot it's time to swap the build plate.
So this is the frame, it's the base of our system. The parts you see in green are 3D printed, where the red are electrical components, and the gray parts are commercial off-the-shelf items. So our frame consists of the linear rods, the aluminum extrusions, and the 3D printed end caps to hold the frame together. So inside the frame here will be the spring stack, and then this is the space we included to dump the build plates when they're done. The gantry will move along these linear rods, which is controlled by this motor.
So this is our gantry system. This is all the components that are actually moving on our device. Here you can see we have the holes for the linear rod. There's also 2 DC motors that control these 2 linear rods. These control our grippers or planks. These planks are obviously larger than build plates so that it can actually hold it. There's also an extra 3D printed beam at the top for stability.
So this here is our spring stack. Underneath each of these, on all 4 sides, we have a hook that is made of 3D printed material, lifting the build plates up. And then we have a retaining arm on each of the pillars, which keeps a single build plate at the top, so our grabber can come in, pick one up, and put it onto your printer.
So this is one of our adjustable feet attached to each corner of the frame. It'll give the system about an inch of adjustability. This way you can ensure that the gantry plate swapper is lined up with where the build plate sits on the 3D printer. The adjustable feet are 3D printed and we'll put them together with a bolt here to adjust them.
This is our control box. This is what holds our PCB and power supply. There is 3 holes here that have LEDs that indicate whether the power is on, whether it is homing, or plate swapping is actually happening. There's also spots for power on and off switch, as well as an emergency stop button.
So this is a visual of the plate swapper next to the 3D printer. You can see here how it'll line up to grab the build plate off the printer, drop it in this space here, retreat back to the spring stack, grab a new plate, and put it on the printer. The system spans about 19 inches wide and 30 inches in front of the 3D printer. Our current design requires it to be placed in between two tables to create that space for the build plate to be dropped.
So the four main electrical specifications for the system are firstly that we need 3 motors, which will be separate motors, and we will be isolating them with relays in order to keep the 24 volts, which we'll be using off of the motor drivers until they're actually in use. And then also we have our 120 volts AC, which will be converting to 24 volts DC for 24 volt DC power supply. We have limit switches, which will be sending signals to the microcontroller to give the position of the machine to the microcontroller to indicate what it is to do next. And then we also have 3 LEDs, which will be used to indicate the status of the machine to the user at any point. Here's an overall schematic of the voltage regulation for this design. Here's our power supply, which is 24 volt DC, 15 amps. And then we also have a voltage regulation circuit with the LM338T. That's going to be used to create the 5 volts necessary to power the microcontroller. And here's the equation used for the regulator output for that design. I built this design and tested it to ensure that it would function properly, and that worked out well. And then I drew 0.3 amps from it, which is like you're not going to be drawing any more than 0.3 amps, and the voltage regulated well. Here's just a depiction of the 3 motors we'll be using. They're all NEMA 17 stepper motors. One is going to be a 2 amp motor to control our linear arm, and then the other 2 are going to be 0.4 amp motors to control the grabbers. Here's an overall schematic of all the connections to the microcontroller. The microcontroller we're using is the TC 4.0. It's represented here by this device X. Here are all of our limit switches. Here's our reset. And then in the corner here is our 3 LEDs to give the statuses. And then we also have 3 transistor circuits, which will be used to switch off and on the relays from the microcontroller, which will be giving a 3.3 volt signal. And then here's the equation showing the base current and then the voltage of the coil. We need at least 3 volts across the coil, and our base current cannot exceed 4 milliamps. So this shows that this design will be able to accommodate that. Here's a depiction of our 3 motor drivers that will be used to control the motors. As you can see here, we have the 24 volts DC coming in at this voltage to the motor pin here. We have an e-stop that will allow us to cut off power to the motors if anything goes wrong. That's represented as the normally closed contact. This is the normally open contact for the relay, which will be isolating the motors when they're not in use. And then we also have the step and direction pin right here, which are going to the microcontroller to be controlled. And then here's our overall circuit schematic. This is the schematic I created in EasyEDA software for the purpose of creating a PCB for this design. You can see here we have the 3 relays. Here's the voltage regulation, our on-off switch is going to go between those 2 points there. And then we also have connectors, and here's our microcontroller and the motor drivers. Here's an overall 2D design of the PCB. You can see here that I have all the connectors on one end for easy access to all the connections to the board, and then our 3 LEDs are also lined up with those for easy visibility on the outside of the electrical box.
All right, so robot logic and operation. Our robot knows its position based on its limit switches. We have 1 at each location it needs to be at. We also have 3 LEDs on it, so in the event a human is home and by our robot, you can tell what it's doing based on which LEDs are illuminated. For robot operation, it's as simple as getting a stack of build plates, loading them into the spring stack, positioning your robot in front of your 3D printer, attaching a clip to the top of your 3D printer, plugging it in, and printing. Here we have a flow chart which illustrates this. So first we start over here, you power up your robot, then it's just waiting. Once that limit switch is hit, we home the gantry plates, the motors turn on, we go get the build plate off the printer, we drop it on the ground safely, and then we reload a new clean build plate onto your printer, move our gantry out of the way, and shut off our motors for longevity.
So we want to make sure that the plate swapper is completely safe for users. So to ensure this, we make sure that there's an emergency on and off stop button. There's also warning labels on each part that is moving, as well as all the main voltages will be covered. For our ethical concerns, we will adhere to NSPE Code of Ethics, Section 1, Subsection 1, which will hold paramount the health, safety, and welfare of the public.
So when we begin testing next semester, we will measure our success based on if the plate swapper can detect when a print is done via the limit switch, then remove the build plate from the printer, drop it out of the way, put a new build plate onto the printer, and complete these actions 3 times using each build plate in our spring stack.
Here's a depiction of our work breakdown structure. We have it divided into 4 different categories, one for mechanical, one for electrical, and then we also have our deliverables and testing. So for the mechanical, we have our frame, gantry, spring stack, control box, and our adjustable features. For the electrical, it's the power system, the inputs and outputs, motors, coding, and then also for our deliverables, we have our presentations, reports, logo, and of course our work breakdown structure. And then for our testing, we'll be testing all the electrical components. We'll be testing the PCB and the various circuits and connections in the PCB. And then we'll also be testing all of our mechanical components. And then once we combine the system together, we'll be testing that to make sure everything functions correctly.
So here's our Gantt chart, or our schedule that we've adhered to this semester. Currently, we are obviously in the final presentation part, but we will continue our material procurement until the end of December.
So here's our cost analysis so far. We started with a budget of $500. So far, we've used $376.01, which leaves us with $123.99. This leaves room in our budget for next semester if we want to make any revisions to our design or if anything might go wrong during this.
So this is our schedule for the past and future. The green items have already been completed, starting this project, finishing out the mechanical design and the electrical design. The red items are what we need to continue working on now and in the future, starting with possibly creating a slide, because as of right now, we are just dropping the build plates as our current idea. Ideally, creating something to slide them off so delicate parts don't get damaged is a good idea. Then we're going to work on our material procurement, as well as designing the prototype, testing the prototype, revising based on the prototype. And then we'll be back here in April for another presentation with everyone else.
On behalf of the Plate Swapper Project, we'd like to thank our senior project peers for their helpful constructive criticism, as well as Dr. Zhu, our advisor. We'd also like to thank Dr. Nye for letting us use the 3D printing lab, and Mrs. Stash and Dr. Bednarz for setting everything up today.
Thank you. Any questions?
Quick question, with the voltage, does it have the possibility of convertibility in case you use it in different countries? Because it's 120 voltage, right?
So we have the system, so it should just plug into the wall, and it should be just 60 hertz, 120 volt.
Can it convert automatically, or you have to use
For other countries.
I believe we most likely would have to use something different, like say the frequency is different, you know. Yeah.
Maybe you could think about that in April.
Sure. Yes, thank you.
Thank you. If you look at the circuit diagram that shows the relay drivers, I'd like to suggest that you need to look at protecting those driver transistors. I don't think that's the one that shows the relay driver transistors. There we go. If you look at those transistors in the upper left-hand corner, there's no diode protection on the relay. When you turn those relays off, That's an inductor that's gonna, the current's gonna wanna keep going, and so you need some diodes on those things.
Okay, thank you.
So emergency project. At the moment, we don't have a plan for dislodging freely the part from the trays that are currently tried.
So we've thought about that, and our advisor, Dr. Zhu, said that it would be very difficult because that's a human job. It's hard to make a robot go soft. It can like go slow, but that way.
So you are putting a new plate and you remove the old one. What do you do with the old one with the parts? You just stack them on top of each other?
Right now, we don't have a completed design for it. We've thought about adding a slide or a basket or a conveyor belt system, but we don't know where we are after testing with our actual budget. So we're waiting till next semester when we start testing to complete that design.
And how many trays have you predicted to be kind of exchangeable? 6, 7?
3. We predict 3 will be enough because an average 3D print can range anywhere from like 1 hour to like 12 hours. And our goal is that you can print 24/7 around the clock, or in some cases, this was originally, the idea came from maybe so a college student could print with all his free time. 8 hours you're at school, 3 plates, plus the one on the printer, that's 4 2-hour prints, that's 8 hours. So you print continuously while you're at school, and then you get home, reload the build plates. But our design, we have enough height that we could put up to like 5 or 6 build plates in there, but we want to start testing with 3 because that will be easier and quicker to test because 3D printing takes time.
I can hear you. All right, thank you. With any automatic system, the most important question is what if something goes wrong? Because that's the whole purpose. It's automatic. So my question to you guys is, what would go wrong, and do you have anything to detect that if something goes wrong? At least to give you a message or give you a warning, you know that. Otherwise, you'll be waiting for nothing.
Yeah, I think it's definitely that into consideration when you're testing. Possibly like the system moving and not being lined up correctly could be an issue, so we could take precautions to try and avoid that. Be able to
You need to, needs to be some sort of detection, some sort of sensor. I mean, this is, again, if you're just designed for a perfect scenario, but if you were like trying to make this into a commercial system, that's definitely part of the, you see, at least they should be aware. I mean, this is going to be hard because to detect what could go wrong, there could be many things. You see what I mean? It's going to be hard, but at least to keep that in mind. Okay?
Any other questions? Okay, thank you.